In our last video, we talked about ionization energy and how the ionization energy changes as you move around on the periodic table. So in today's video, we're also going to continue to talk about the periodic table. That might be the worst periodic table I've ever drawn in my entire life, but we're going to go with it. And we're going to talk about the same patterns. What happens when you go left to right across the periodic table, and what happens as you go down the periodic table. So the next pattern that we're going to talk about does not have to deal with adding electrons or taking electrons away. So when we talked about ionization energy, we're talking about how much energy it took to remove an electron from an atom. Okay, the next thing we're going to talk about is we're going to talk about how big or small an atom actually is. And when we talk about how big or small an atom is, we're talking about its atomic radius. So again, let's break those words apart. Radius is just like any type of circle. The radius is the distance from the center of the circle out to any point that should be the same distance if I knew how to draw a circle really well. Okay, so the radius is the distance from the center to any edge, and atomic just means atom. So it is the radius of the atom, or again, how big or small an atom is. Obviously, if an atom has a large atomic radius, we say the atom's big. And if the atomic radius is small, then we say that the atom is small. And again, just like ionization energy, there are some patterns we can look at as you go across the periodic table. So, and the nice thing about this is that what we learned about ionization energy applies directly to the sizes of the atoms. So, as you go from left to right across the periodic table, the atomic radius, or the size of the atom, decreases. That's a real tough one for students to understand because you're going from number 3 to number 4 to number 5 to number 6, number 7, number 8, number 9, number 10. Okay, as you go across the periodic table, what happens to the atomic numbers? They get bigger. Okay, there's 3 protons, then 4 protons, then 5 protons, all the way up to 10. And then you go to the next row and it's 11, and then 12, and then 13, all the way up to 18. And so as you go across the periodic table, there's more protons. And if there's more protons, that also means there's more electrons. Shouldn't that make the atom get bigger? Again, let's think about what does more protons mean. Okay, more protons means more attraction. Okay, so there's an increase in the number of protons, and therefore that means there's more attractive force between the protons and the electrons. And again, this is the same reason for ionization energy, right? As you go across the periodic table, the number of protons increases, so the attraction to the nucleus is greater, so it takes more energy to remove an electron. Okay? That's the exact same reason why atoms get smaller. The atomic radius, again, decreases as you go across the periodic table because there's more protons as you move across the periodic table, and more protons means more attraction. And again, since the valence electrons are all in the same shell, that's our other thing we're looking for there, valence electrons found in the same shell, we're not adding any more shells of electrons to the atom. So therefore, the electrons are in the same shell, the second shell, the third shell, whatever shell you're in. Anytime you go across the periodic table, you're staying in that same shell. So therefore, the number of protons is the more important factor here. Okay, so as you go across the periodic table, atoms get smaller. They get smaller because there is more protons as you move across the periodic table, yet the valence electrons are all staying in the same shell. Okay, let's look at an example of this. Okay, the atomic radius of Al is 1.18 angstroms. Oh, I don't know what angstrom is. Who cares? Okay, it actually means 1 times 10 to the negative 10th meters. But again, that doesn't matter. Okay, don't let things like that trip you up. All that you're noticing is that the atomic radius of aluminum is 1.18, chlorine's 0.99. All you're noticing is that chlorine is smaller than aluminum. And you just have to say why. Okay, they're telling you the answer. They're not saying which one is smaller or bigger. They're saying chlorine is smaller than aluminum is. And then you just have to say why. Okay, here's the answer. And here, again, I'm going to underline the parts that I'm going to look for in your answers. Chlorine has a smaller atomic radius than aluminum because a chlorine atom, so chlorine has more protons than aluminum. And so the attraction to the nucleus is greater. And since both atoms' valence electrons are in the same shell, the greater number of protons in chlorine make its atoms smaller. Okay? So example number 2 says oxygen atoms are smaller than carbon atoms. So I'm going to try to write my answer in a different way, but still saying the most important parts. So again, they're telling us the answer. They're not saying true or false. They're saying oxygen atoms are smaller than carbon atoms. Now why? Because, and again, I'm trying to not, up here I wrote a really, really long answer, but I'm trying to show you can do the same thing by writing a lot less, okay? Oxygen has more protons than carbon, so oxygen has more attraction, and oxygen and carbon, and now I'm looking at the periodic table, I'm looking at where their valence electrons are. Both have valence electrons in the second shell. See how I kind of said that differently from above? Okay, above, okay, it said that the valence electrons are in the same shell. So here I just identified what shell that is. Did I have to say that? No. Could I have just said again like above, oxygen and carbon are both their valence electrons are in the same shell? Sure. Okay? And that is perfectly, because again, that's what I'm looking for. And valence electrons in the same shell, that's what I'm looking for as well. Okay, now as you go down the periodic table, what happens to the ionization energy? The ionization energy goes down. Why does it go down? Because the valence electrons are farther away from the nucleus. There's more electron shells. There's more inner shell electrons. Okay? And so same thing with atomic radius. As you go down the periodic table, think about this. Here's the first shell. Here's the second shell. Here's the third shell. Here's the fourth shell. What am I doing? As you add more shells, what happens to the size of the atom? Of course, the size of the atom increases. So as you go down the periodic table, the atomic radius increases, which means the atom gets bigger. Okay? Now, what are the important parts here? Okay, there are more electron shells that are farther away from the nucleus as you go down the periodic table. Okay? And more electron shells, there has to be space for them. Of course, that's going to make the atom bigger as you go down the periodic table. Okay, so example 3 here. Phosphorus atoms are larger than nitrogen atoms. I look at the periodic table. I see that phosphorus is below nitrogen. Okay, and okay, so I'm like, okay, yeah, that makes sense. Yeah, phosphorus should be larger. Why is that? Because phosphorus atoms, so P atoms, have more electron shells that are farther away from the nucleus than nitrogen does. Okay, and here we can say P has more, and again, remember, shielding electrons is the same thing as inner shell electrons, same thing as the core electrons. Lots of different ways to refer to, here's the nucleus, and then here's some electrons, here's some electrons, here's some electrons, and then here's our last shell of electrons out here, okay? So these 1, 2, 3 electrons are all valence electrons. Valence. What about all these other electrons that are in here that are between the valence electrons and the nucleus? Those are what we call the shielding electrons because they're kind of blocking the attractive force of those valence electrons. You can also call them inner shell, you can call them core. They're all the same. The important part is they're not valence electrons. Okay, so example 4 here. List the following atoms in order of increasing atomic radius. Increasing, again, means start small and go to big. Okay, if it's increasing, that's what that means. So I'm looking at the periodic table. We got F and O up at the top, and then down below we have I and we have TE. Okay, so clearly we're going across the periodic table and then we're going down the periodic table. So we want to start with the smallest of these. So hopefully you see right away, okay, these are farther down the periodic table. They're going to be bigger. Okay, so these ones up at the top are going to be smaller. Which of those two is going to be smaller than the other one? Remember, as you go across the periodic table to the right, atoms get smaller because more protons, valence electrons are in the same shell, the attraction is stronger. So fluorine of those four is the smallest. Okay, and then the next one would be oxygen. And then the next one, again, now those are taken care of. Now of the bigger two, which one's smaller of those? Remember, as you go across, they get smaller. So the smallest one of those two would be iodine, and then the biggest one would be tellurium. Okay? And again, we explained that already. As you go across, more attraction. As you go down, more electron shells. Okay? And then we can actually see our answer here and make sure we're right. Fluorine, we said, was the smallest, 0.71 angstroms. Then oxygen, 0.73. Okay, and then as you go down the periodic table, there's iodine, way almost double in size, 1.33, and then tellurium is 1.35. So again, like ionization energy, as you go up and to the right, atoms get smaller. So helium is the smallest atom on the whole periodic table, even though it has more protons and electrons than hydrogen does, because both of those atoms, think about hydrogen and helium, they only have electrons in the 1s subshell. And since helium has 2 protons and hydrogen only has 1, there's more attraction. That's going to bring those electrons in a little bit closer. So smaller, and then again down in the bottom left is bigger. Okay, and that is what we're going to discuss here in terms of atomic radius. In the next video, we're going to talk about what's called the ionic radius, which is where you have a charge on those particles.